So up until now, we've been really worried about having absolute values when you pull something out of a even numbered root. And what I'm going to say is from now on, forget it. Don't worry about absolute values for anything anymore. So to be clear, if you have something like this, I don't know, how about 2? How about x to the third? We're actually, let's just do this. Let's do x to the 5th. What we've been doing up until this point, actually, no, that won't work either. Let's just do it as 2x, yes, to the 3rd. Sorry. So up until now, what we've been doing is something like this. We've been saying, okay, this is the same thing as 2 with an x squared and then times another x. And when we get to pull one of these guys out, right, because it's, I'll try to remember something in just a second. So we get to pull that out as 1x. And what we've been doing up until now is because it's being pulled out of a square root, we do it in absolute value, leaving this guy right there. From now on, forget it. We are not going to worry about absolute values. I'm going to go into a little bit why in just a second. One thing I just remembered. Last time we were doing an example and we had something like this. We had the square root, and I think there was a 2 out front, and there was a 4 in here, and there was like an x or something like that. And when we pulled out the 4, first off, how would I simplify this right here? I should pull what out of here?
A 2.
A 2. In class, we pulled it out as a 4. It was an oversight. And I noticed it after it was too late, after it was already on YouTube.
I thought we just skipped a step and multiplied 2 times 2 and then got 4.
Yeah, that's probably what happened. I don't remember exactly what it was, but I noticed it after the fact and it was too late to edit the video. And I was just like, So we're on the same page. We know that if it's a 4, we pull it out as a 2 and not a 4, whatever. Okay. I just wanted to say that. So, okay, the reason why we're not going to really worry about absolute value anymore is for a couple reasons. And first, let's just look at this. If I have this, okay, in this case, first off, what does x have to be?
3
or
-3
or -3, right? The idea is, that with something like this, you're squaring a number. Of course, you're getting a positive number, and there are 2 possibilities for that. And the reason why is, if you think about what a parabola looks like, here's the parabola y equals x squared. When you plug in a 3, you get out a 9. But when you plug in a -3, you get out a 9. And so you're saying you plugged in some number, x, and you got out a 9. Well, there's 2 possibilities. Either it was 3 or -3. And so okay, in that case, when we do this, and the way that we're going to go about solving equations like this is we're going to take the square root of both sides. And when you do that, whenever you take a square root, just by what it means to be a square root is that there are 2 numbers, the positive and the negative one, that make that true. And so we're going to get in the habit of whenever we're starting, in fact, I'm going to write this over again. Whenever we're starting with an equation like this, and one of our steps is to take a square root of both sides, we're going to get in the habit of, as soon as we do that, we're going to put a little plus minus right there. Because that means that it's either the positive square root, the principal square root, or it's the negative of whatever that is. In which case, this guy comes out to be just a plain old x. And then this is a plus or minus, what's the square root of 9?
2, 3.
3.
Wait, yeah.
Yes, square root of 9 is 3. And so this is in practice how you're going to do this for the rest of your life. Whenever you have an equation, you go to take the square root of both sides, what you're going to do is just take plus or minus that thing. Now, what the book has been doing, and the way that it's been doing it, has been to say, well, this right here, the square root of something, well, that's the absolute value. And then we take the square root of that and get 3. And so the absolute value of x is 3. Well, that means that x is either itself positive 3 or it's negative 3. Whoa, he's really into Elmo's world.
Wow.
Wow. So, so this, yes, this is, and so in this case, this is true that it is the absolute value that you're looking for and stuff like that. And we could go along with it that way, but in practice, it's much easier to just remember when you're starting with an equation and one of your operations is to take a square root of both sides, we have to consider both the positive and the negative answer. So we're going to get in the habit of whenever we take a square root that we just write plus minus in front. And that's going to be what we do from now on. And so now this is where, so, okay, so that's on one side. This is why we're going to forget about absolute value. The other reason we're going to forget about absolute value is this. Let's say we have an equation that's like this. The square root of x is equal to 3. What does x have to be? The square root of what is equal to 3?
9.
9. I chose this for a reason. So yeah, you know it's 9. It's not negative 9, right? It has to be positive 9, right? Like it has to be. And then in practice, what we do is we have a square root. So over here, we had something squared equals 9. We're trying to get to that x by itself. So the way we undo square is to take a square root. The way to undo square root is to square it. They're inverse operations of each other. And so what you're going to do in this case is say, okay, I have this. I'm trying to get x by himself. And so I'm going to square that thing. And so you take whatever that number is and you square it. And so you have to do the same thing to this side right there. And so now this is where it gets a little tricky. Is that, well, what this means is you've taken the square root of x multiplied by itself. So that's the square root of x times the square root of x. And I'm just going to go ahead and write 9 over here because 3 squared is 9. And now if we're just going along with the way that the book has been doing things, we'd say, okay, something, a square root of something times a square root of something is the same thing as the square root of the things multiplied by each other. Do you have something to say?
No, I just realized the problem.
Cool. Cool. So then we do this and we say, okay, this, the way the book has been telling us is that we do this. Okay. And so now if we go along with what the book says, we'd say, well, wait a second, square root of something squared has to come out as a absolute value. And so we'd say, okay, well, then the answer is the absolute value of x is equal to 9. If the absolute value of x is equal to 9, that means that x itself is either positive 9 or negative 9. So we have an answer of plus or minus 9. In other words, what we're saying here, what this right here says, is that x is either equal to negative 9 or x is equal to positive 9. But if we look back at the very beginning, just the context of the problem, we know that x can't be negative 9, right? You can't do that. Well, you can, and we're going to deal with that later. We're going to take square roots of negative numbers. But at this point, I can tell you no matter what, if your answer is a positive 3, right? We know that you took the square root of a number and you got out a positive 3. Well, then you couldn't have been the square root of it. Damn it, of course it did. Of course it did. We're going to hope that it's not going to do this more than once or twice.
I also have a question.
Yes.
What I guess I could be completely and totally wrong, but wouldn't you do what's in, like, solve what's inside the parentheses first? So like if you have the square root of x, oh,
Still not happening. Okay, we're just gonna forget this. Give me just a second.
okay.
Right. And here we go. Okay, so what were you saying now?
So then if you have the square root of x
Mhm.
and x is not, or the square root of 9, for example, which is 3,
Yes,
right? Which we did earlier, right?
that's the one we did earlier. Yeah, we took the square root of 9 and found, but there's a subtle difference here, right?
But if you then you have the parentheses and an exponent, wouldn't you do what's in the parentheses first and then square that?
You mean this right here, what's in the parentheses first?
Uh-huh.
So we don't know what the square root of x is
Oh,
in this case.
right.
Trying
Okay.
to find out. And the reason that we took this step, the reason that we said, okay, square this guy out, is because we're trying to get x out, trying to get x by himself. And the way to undo whatever this is, it's kind of like if you had an equation like this, 2x equals 5, x is not by himself. So the thing you do to undo multiplication is division. And so you say, okay, I'm going to divide to undo that multiplication. In this case over here, we have square root of x equals 9. And so in order to undo square root, we have to square because that's the opposite of square root. And so what we're doing here is we're taking this and squaring it. And so you're saying, like, do what's inside the parentheses. Well, yeah, but we don't know what to do. If we knew what to do inside the parentheses, then we wouldn't need to have done that in the first place. It's that I'm taking this step in order to undo this.
Okay.
And so, and now another way of doing it, another way of seeing this, that where we're not even using parentheses, is it's kind of like saying, well, right here we have something like a equals 9. And I can multiply both sides of an equation by any number. And so, for instance, I can multiply both sides of the equation by a, if I were so inclined. I could go ahead and multiply both sides by a, in which case I would have, but then, oh, wait a minute, but a was equal to 9, right? So over here, I could just say, well, a is the same thing as 9. And so I have 9 times 9. And over here, I have a times a, or a squared, something like that. That's kind of what we're doing over here. I'm just using shorthand for that. I'm saying since the square root of x is equal to 3, then I could multiply both sides of this equation by the square root of x. So I'm going to do that. Multiply by square root of x. Multiply this side by square root of x. But we just said that the square root of x is actually equal to 3. That's what we started off with. So instead of writing it as the square root of 3, I'm just going to, the square root of x. We said in the beginning, the square root of x was equal to 3. So when I do it on that side, I'll write it like this. When I do it on this side, I'll write it as 3. And that's ultimately what we're doing. I'm just kind of showing it as square both sides here. And so it's not really that there's something in the parentheses. It's that I'm trying to make this operation right here, where I multiply both sides of the equation by something. That's Kayla. That's right. I'm sorry, buddy. I'm sorry. We got to teach. And so that is what's going on here. That gives me 9 over here. And then we have this times this, which is this right there. And that's what we're doing. Now, the point that I'm making, though, is that if we follow, so did that make sense, what I just said?
Yeah.
So the point that I'm making is this is what we do. Like this, if you have an equation like this, in order to get x by itself, you square both sides. And ultimately, it looks like this. But if you follow along with the book's reasoning, the way that the book has been training us to go, it's going to say, well, this is that, that is that, and that's the absolute value of that, leading you to a conclusion that apparently if you plug in a -9, this says that the square root of -9 is equal to 3. Well, that's not true. That's not true at all. And so we're going to forget about this whole absolute value thing. Because in practice, and this is what it looks like in practice, like this is what you do here. You're just going to say, if we forget the way the book said to do it, and we go right here, we'd say, well, squaring a square root is the thing that makes that thing pop out. Like we're undoing this, right? Like here you squared something, you undo it by taking a square root. Here, you took a square root, you undo it by squaring both sides, giving you the thing that was inside, just by itself. And then you find x equals 9, which is what we expect. That's the only way that that works. The thing to keep in mind is that when you go the other way, when you take a square root, there are two possibilities. That yes, it is the case that -3, plug that into the original equation, -3 squared does indeed give you 9. And +3 squared does give you 9. But in this case, you don't end up with two answers. It's kind of impossible to go by the same reasoning to get two answers because well, you don't take the square root of -9 and get a +3. That doesn't happen. So long story short, we're going to forget about absolute values and stuff. Tonight in your homework, you're going to have some problems that in the back of the book, it's going to have absolute values. Forget about it. So if the back of the book says that the answer is absolute value of a plus 2, and you got your answer says just a plus 2, that's what we're looking for. Your answers are going to look like this. Pretty much when the answers in the back of the book say it's absolute value of something, forget it. Just pretend those absolute value bars aren't there. And when we get to complex numbers, which is coming very soon, you will see why I am no longer going to make this distinction. Hold up, I got to change Pete's stuff. Otherwise, things are going to get loud here in just a second. All right. Okay, bud, give me just a second. There we go. So, okay. Okay, can I erase this stuff?
Yeah.
Long story short, forget about absolute values for now. I did want you to see them because you may very well run into a standardized test one day that says, simplify this. And then there's a bunch of multiple choice answers. One of those multiple choice answers is, how about 2xy root x? And one of them is 2xy absolute value root x. You'd know, oh yeah, that's right. There was that stupid thing about absolute values. And so when you're doing your multiple choice test, you would say, yeah, that's the one I'm looking for. I think I did that right. Yeah, pull out 1x, 1y. Okay. And so it's good to know in practice, you're never going to need it. Like you're never going to need to consider it in practice, because in practice, we take care of that by saying, whenever you take a square root, you get a positive and a negative answer. And so when you have something like this, you'll say, okay, I need to undo square, which means take a square root. And when I take a square root, I get a positive and a negative answer. That makes that guy come out. And then I have a plus and minus. Square root of 81 is 9. And so I have two answers. X is -9 and X is positive 9 right there. And so, yeah. And when we get, there are, yeah, in fact, going along with the using the absolute value the way the book does will lead you into something that is absolutely wrong. And I'm surprised it's in the book. And so we want to drop it. I did want you to see it so that you've seen it now. And for the rest of your life, forget about it, because forget mostly about it. But we're not going to be using it. And so from now on, forget about having absolute values with stuff. Okay, we good?
Yep.
Okay, so what we're talking about today are more operations with radicals and stuff like that. And so one thing I want to get into is just some very simple stuff. If we have something like this, the square root of 3. I'm sorry, buddy, I gotta do stuff. I know, bud. So you're going to have stuff like this. And this is exactly what you think. You have a number multiplied by a sum. We got to distribute this guy over. And when he distributes over, we usually, yes, this is the square root of 3 times 4 plus the square root of 3 times the square root of 3. But what we usually do is we like to write numbers that aren't square roots on the left-hand side. And so we would write this as 4 square root 3 plus, what's the square root of 3 times the square root of 3?
Same thing as 3 times square root of 9.
Square root of 9, which is what?
Are you, wait.
3. And from now on.
Oh, you wait.
Yeah, the square root of 3 times the square root of 3 is what you told me. It's the square root of 9. And what's the square root of 9?
3.
Just 3. 6, 9, 6. And so there's that. From now on and forever, whenever you have the square root of x times the square root of x, it is just x.
Oh.
Well, because the square root of x times the square root of x is just the square root of x times x, which is x squared. And so you're undoing what you've already done, and it brings you back to x right there. Again, we're not worried about absolute values anymore. Doesn't matter if x was negative to begin with or positive to begin with. This is always going to be true.
Okay.
So when I see this right here, the square root of 3 times the square root of 3, I don't really need to use my brain. I can just say, oh, the square root of something times itself is by definition 3. Like that is what it is. So you're going to see some stuff like this. This is pretty straightforward stuff. What's less straightforward is when you have something like this. Let's do 1 plus the square root of 5 squared. Guess what we have to do with that? We have something plus something, quantity squared.
Oh, great. Wouldn't you have to factor it out or whatever? Multiply it out.
Foil.
Yeah.
Foil it out. So something squared is whatever that something is times itself. And so be careful with that right there. And so we have 1 plus the square root of 5 times 1 plus the square root of 5. Okay. First, outer, inner, last. What do I get for first?
1. Wait. Yeah, just 1, right?
1? Yes. Sorry, I can't hear you over screaming memers here. Outer gives you what?
The square root of 5.
Just plain old square root of 5. And inner gives you what?
Square root of 5.
Plain old square root of 5. And the last gives you what?
5.
5, right? Because the square root of something times itself is by definition whatever is inside of there, right? So I really want to drive this point home. Square root of smiley face times the square root of smiley face is what?
Smiley face.
Smiley face. Whatever goes inside there is the thing that pops out. That's how you make that thing pop out, right? So all together now, we usually like to write this in the same form. We like to have our plain old regular numbers out front plus something involving a root. So how do I rearrange this to give me that order?
Well, you'd have 1 plus 5 or 6, I guess.
6. There you go.
Plus the square root of 5 plus the square root of 5,
Which
which
is
is the same as hold on.
What if I had x plus
Would
x?
that be the same as the square root of 10? Because
I think so. Because it's not the case that x square root of x plus square root of y is equal to x plus y. That is not true.
right. Would it be the wait, hold on. 2 square root of 5?
2 square root of 5. Yep. 1 apple plus 1 apple is 2 apples, right? So it's the same kind of idea now. Like we've trained ourselves pretty well to see stuff like this. If you have 6 plus 2x squared plus 3 plus 4x squared, we've trained ourselves pretty well to say, you have a total of 6x squareds. It's the same idea here. We could, if we were to think about this as our unknown or whatever it is, right? Then we'd say, oh yeah, you just add those together. How many square roots of 5 do you see? Well, you have a total of 2 of them. And so, for instance, so that is the answer to this. That's how you do that type of question.
Mm-hmm.
If we had something, say, like this, 1 plus 3 times root 7 plus 6 minus, how about, I don't want to do, I want to do plus root 7. Then we'd say, okay, what is this? You tell me how to simplify this guy.
So that would be 1 plus 6 is just 7, and then plus what, 5 square root of 7?
There you go, 5 root 7s. Because really, right, that just 3 root 7 means take root 7 and add it to itself 3 times, whatever that is. And then this says you do that 2 times. Okay, so add on 2 more 7s. I have a total of 5 7s, and yeah, it all means the same thing, right? So, okay, so that's how we deal with those. That's in your home, stuff like that is in your homework. Pretty straightforward stuff. Again, we are not worried about absolute values. Your book is going to have absolute values in the answer. Just forget about them. Forget about them altogether. So, and I'm not just being flippant here. Like you'll see when we get into complex numbers, I will prove why we are forgetting about absolute values altogether. And again, in practice, you really don't need to worry about them. So we're not gonna make a fuss about it. Okay, another thing now that is some people are real sticklers about rationalizing the denominator of something. So for instance, if we have an expression like this, I'm just gonna go ahead from now on and we're going to think this is the same thing as the root 6 over root 5. Okay, like we should be able to go back and forth between these as necessary, right? Sometimes we'll be doing something like this and it'll be easy to go in the other direction. Like for instance, if it's root 30 over root 5, I might say, well, wait a second, I know that 30 divided by 5 actually reduces, right? And so it might be to my benefit to write it like that, and then say, oh, wait, what's 30 divided by 5?
6.
6. And so in that case, I just made my life a lot simpler. So that's one case where we might want to go in this direction, right? And so that's cool. But we also sometimes going in the opposite direction will be good. So whenever I see something like this, I'm thinking kind of both of them and seeing which is going to be more advantageous to me, whatever. If you're given something that looks like this or looks like this, either way, and you're told to rationalize the denominator. What we mean is, so first off, the square root of 5 is an irrational number. It means it cannot be written as a ratio of two integers. It is not a terminating or repeating decimal. And sometimes it's advantageous to not have irrational numbers in the denominator. Quite frankly, I don't care. I've never seen an instance where having a irrational number or a square root or something in the denominator has ever hindered me. If and when you go to take trig, you're going to see a bunch of stuff like this, and it's way easier to just keep it like this and not rationalize the denominator. So, but when we get to complex numbers, it's very important that we can do essentially what we're going to do right here. Only, to basically get complex numbers out of the denominator. And so this is good practice to get us ready for doing that with complex numbers. So I say, let's just plug ahead and do it. The idea here is we need to rationalize the denominator. The denominator itself is square root 5. And what did we just say about what can we multiply this guy by to turn it into a nice number that we like?
Itself.
And we can multiply it by itself, right? And so if I take this number and I want to make, if I have this root and I want to make this number pop out, the way I do it is just multiply it by itself. It's that easy. And so, again, I don't want to change this. And the parallel that's going on here is kind of like I have 3/2, but I only have a 1/4 teaspoon. And I need 3/2 of a teaspoon of something, but I only have a 1/4 teaspoon. So I need to change this into quarters for whatever reason. And so I say, well, if I multiply the top and the bottom by the same thing, I have not changed this number at all. I'll still have 3/2. And I would rewrite this as 6/4. And indeed, yes, 6/4 is still equal to 3/2. I've just changed the way that it looks, right? This is the same game right here. We need to change the way this looks, but we don't want to change the overall fraction. And so I'm going to multiply this guy by 1. It's the only way to multiply by something and not have it change. And so please tell me what I need to write here in order to get rid of the 5 and not change the fraction. What goes down here?
The square root of 5.
Square root of 5. Therefore, what goes on the top? It needs to equal 1.
Oh, square root of 5.
Square root of 5. It has to equal 1. This is going to be the name of the game. Just like when I had 3/2 and I needed to multiply the denominator by 2 in order to change that into a 4, I could say, well, as long as whatever I put on the bottom is whatever's on the top, that's the same thing as 3/2 times 1. And so it's still equal to 3/2. And so the key here is, how do I write 1 in a way that's going to help me out? And so ultimately, when you're rationalizing the denominator, this is all you're doing. You're just finding what number will turn that into a rational number. In other words, what's going to make that 5 pop out? Well, multiplying by root 5. but I can't change the overall fraction that we started with, or the overall number that we started with. And so this has to be root 5 over itself. It has to equal 1. And so now what we've just done is we've taken root 6 times root 5 on the top. What's root 5 times root 5?
5.
5. And so what do you want to do now? I mean, technically we're done. That is a rationalized denominator, but what we usually do is try to combine everything together. And so how could I rewrite the top a little bit simpler?
6 times 5 is 30 to the square root of 30.
Square root of 30. There we go. Now you might be tempted to say, wait, 30 is divisible by 5. Yeah, but no, because that's the square root of 30. That has nothing to do with plain old 5. When they're together, when they're in the same thing, then yes, you could do some kind of cancellation and stuff like that. But up here, like, the whole reason we did this was to get this guy to be a plain old 5. And so that's the idea there. That's what we want to do. Let's see. So that is how you rationalize a denominator with something that looks like this. I do want to do one more of these guys, because with square roots, it is so straightforward, right? If I have, oh, I don't know, 1 over the square root of 7, what do I have to multiply the bottom by to get rid of that root 7?
The square root of 7.
Square root of 7. So what has to go in the numerator?
The square root of 7.
Square root of 7. And so I have 1 times the square root of 7 is just the square root of 7. And what's in my denominator?
7.
Just plain old 7. That's why we chose that in the first place. I chose the thing that's going to make that 7 pop out. And so yeah, 1 over the square root of 7 is the same thing as the square root of 7 divided by 7, right? It's really straightforward when you have square roots, because really there's only one way of doing it. But when you have cube roots or other orders of roots, they can get a little bit more tricky. So let's take a look at this. The cube root of 3/9. Now, if you want, you could just go ahead and say, in fact, yeah, let's not make it, let's make it a little bit better. Let's make it 2/9. That way there's not that ambiguity, like, should I divide it first? Because you could, and you'd end up with the same answer. But in this case, 2 and 9, they don't divide. There's nothing we could do there. But what I'm going to do is say, okay, 2 and 9, I need to rationalize the denominator. That thing is the same as this, 3 root 2 over the cube root of 9. And you might think, oh, we'll just multiply it by the cube root of 9. But you'd be wrong, because this is not a square root. This is a cube root. And so now this is not the way we're going to go about doing this. So, but just so we know, if you have a cube root of some number, let's call it a, it's not squaring that undoes that, right? It's cubing that undoes that, right? Because that's what a cube root means. It means you take something and multiply it by itself 3 times. So you would need a total of 3 of them. You multiply this guy by itself 3 times, right? Whatever number is there, that's how many of them you need in order to make that thing pop out. And so you might be tempted to say, aha, okay, well then I'll multiply the bottom by 2 more of these guys. We'll have cube root of 9, cube root of 9. We'll do that on the bottom, we'll do it on the top. But that's kind of like overkill in this case, because we could rewrite 9. 9 is what? How can I rewrite 9?
The square root of 3. No, sorry. Whoa. Look.
Please.
9 is what times what?
3 times 3.
3 times 3.
Please.
Oh, 3 squared.
3 squared. Yeah. And so now here's another principle here, is that this that I just wrote over here, we can rewrite this way. In other words, as soon as you have 3 of whatever it is in a cube root, right, you get to pull one of them out. You've seen this in homework a bunch of times, right? Like you have the cube root of 2x to the 5th times y cubed. You could say, as soon as I have 3 of them, I get to pull one of them out. And so this right here, the cube root of 2 times x to the 5th is x cubed times x squared, y cubed. And so you say, I have 3 of these guys together, I get to pull one of them out. 3 of these guys together, I get to pull one of them out. And so I'm left with 1x, 1y, cube root of 2x squared is what remains inside. It's the same thing here. It's just that we're deficient only by one of these cube roots of 3, right? So in other words, I only need one of them to get the job done. I don't need to go and multiply by another 2 sets of these 3 times 3s. I'm just missing one of them. And so what I'm getting at here is I don't need to go overboard in order to kill that guy. I just need to bring one more 3 into the mix. And since we don't want to change this number, whatever we write in the denominator has to be the same as what we put in the numerator. What does the numerator have to be?
The cube root of 3.
Cube root of 3. And so in the numerator, I have the cube root of 2 times the cube root of 3. And in the denominator, I don't need to write this down, but I just want to be explicit. What I've done is I've just turned this into the cube root of 3 times 3 times 3. In other words, I have 3 of them. That means I get to pull one of them out, right? What I have now is 3 to the 3rd power. And so this reduces to cube root of 2 times cube root of 3 all over just 1, 3. That makes sense?
Yeah.
So it's, similarly, like if I had something like 2 over, let's say, the 7th root of 2 over the 7th root of, how about, no, let's use 5. 5 to the 5th power. How many more 5s would I need to undo the 7th root?
Five, 7 of them?
Do I need so I need a total of 7 of them. And so how many do I need to add in right here? Because I have 5.
Oh, hold on. That looks like a 2. Sorry.
Oh, man. Sorry.
So then you need 2 more.
You would need 2 more. And so I would say, okay, in order to be able to pull out 1 5, I need a total of 7 5s. And so I'm deficient a total of 2 5s. So whatever I do on the bottom, I gotta do on the top. And then I'd say, yes, this is the same thing as the 7th root of a total of 7 5s. 5 to the 7th. Now we have the 7th root of 2 times the 7th root of 5 squared. The whole reason we did this was not to go overboard, to just give us as many 5s as we need to be able to pull one of them out. And so the denominator reduces down to just plain old 5. The numerator, I guess we could write as the 7th root of 2 times 5 squared, which is 2 times 25, which I guess is 50. So I guess if you want, you could write it as 7th root of 50 over 5. So that would be a rationalized denominator. If you want to stop short and just say that, that's perfectly fine too. Because I could see that you don't have 7 of anything. You can't pull out anything else. And so whether you write it like that or you write it like that, it's the same thing. The point is that we have now rationalized the denominator. Okay. So pretty straightforward. You're just looking at what is my order of root? How many things do I need in order to be able to pull one of them out in order to kill this root altogether? And then you just multiply the top and the bottom by that thing and you're good to go. It gets difficult here in a second. So can I erase this stuff?
Yes.
Okay. Now we still want to rationalize the denominator here. And what I'm going to do is, let's do it this way. We have 3 divided by the square root of 2 plus the square root of 5. Uh-oh. Uh-oh.
Oh boy.
Now we have a problem because it used to be easy. If it was just the square root of 2, you'd say, oh, I know what to multiply by. I was multiply it by the square root of 2 and it'll kill it. Here's, if it were just the square root of 5, you'd say, I'll just multiply by square root of 5 and it'll kill it. So you might think, I'll just multiply by the square root of 2 and the square root of 5. And you'd be wrong. Let me show you why. Because if you tried that, let's say, and so I'm just looking at the denominator right now. You really don't need to write this down. Just watch what happens. If I said, well, maybe I could get rid of this and turn it into a nice rational number by just doing both of them. I'll just multiply by the square root of 2 times the square root of 5. Let's see what happens. This number, this one number, that times that, will jump over here and jump into here. And we'll end up with, this first one is square root of 2 times square root of 2 times square root of 5. Okay. This jumps over, and I'll even write it nice. I'm going to write this on the left-hand side. So we get the square root of 2 times the square root of 5 times the square root of 5. These guys do kill each other because that was my intuition. It's like, well, I got to get rid of that guy. I'm going to have to multiply by a square root of 2. And so a 2 pops up. But I'm left with this square root of 5. Over here, yeah, that guy took care of that guy. Those go away. We end up with just a 5 right there. And so I have the square root of 2 times 5, but I like to write my 5 over here. Oh, I'm still kind of in a bad way. Like, had I multiplied the top and the bottom by this, I would still have these roots in there, and I wouldn't be able to get rid of them. So what do we do? Well, there's a trick. Now you want to start writing again. So there's a trick. And once you know this trick, you could use this trick for the rest of your life. The trick is to multiply this thing by what we call its conjugate. And all that is you write the thing the exact same way.
Oh gosh, yeah.
But you flip the sign. If the sign between them is positive, the conjugate is negative. If it's negative, you write it as positive. It's like a twin, right? Like you don't just have a twin. You have to have 2 things to have a twin, right? If A is the twin of B, then B is the twin of A, right? It's a symmetrical relationship, right? And so that's this kind of thing. This is the conjugate of that, and that is the conjugate of this. They're both conjugates of each other. They're like twins. And now let's first outer, inner, last, and see what we get. What do I get with first?
The square root of 4 Or no, 2 times I guess you just get 2.
Just get 2. Let's, from now on, when you see a square root times itself, that is what makes that number pop out. Remember what we said earlier. Square root of smiley face times square root of smiley face is smiley face. Okay, so that is how, that's why we did it, right? That's why we chose this number here, is because it makes it pop out. Okay, so outer, what do we get when we do the outer multiplication?
Minus 2 square root of 2 times the square root of 5.
There we go. Right, we don't really need to simplify this. We can leave it like that. What do we get when we do the inner multiplication?
Plus the square root of 2 square root of 5.
And what do we get when we do the last multiplication?
Minus 5.
Minus 5. Now check this out. This is the cool thing about conjugates, is because we wrote the exact same thing here, the outer and the inner will always cancel each other out. Right? Plus this amount minus that exact same amount comes out to nothing. And this is how we get rid of all of those pesky square roots. And so altogether then, this comes out to that. That's 2 minus root 5, which is minus 3. And that is a rational number. That's perfectly good. And we're trying to rationalize this denominator. So let's do this all together here. I'm going to get rid of this stuff. Can I get rid of this stuff?
Can I have 1 second?
Yep.
Yes.
Okay, so getting rid of this. We are to rationalize the denominator. So I know that I have to multiply this by 1. But I'm going to write 1 in a way that actually helps me out. So what is the thing that makes these go away? We just did it. What's the conjugate of that?
2 minus 5.
Root 2 minus root 5. And
Right.
so it has to go on the top.
The same thing.
The exact same thing. It has to. Otherwise, we've just changed this number. But right now, we just took the original number times 1. Good to go. Nice. That's still the same number. So what do I get in the denominator? And at this point, you should notice that you chose this because you know that the outer multiplication and the inner multiplication will always cancel each other out. So we don't need to worry about what is the outer and the inner. We're just going to, when we FOIL this guy out, let's just do the first. What's root 2 times root 2?
2.
Just 2. And then the outer and the inner cancel. We should be able to just look at it and see it. We also know that that's why we chose it in the first place. Now, here's something to notice. You've just multiplied 2 conjugates together. And the conjugates, like by definition of a conjugate, like that has to be the opposite sign as that. So is my final thing going to be a positive or a negative number?
A negative?
It's always going to be minus, always, because the conjugates always work that way. It will always be whatever that is minus whatever that is. And what is it? What do I get when I multiply root 5 by root 5?
Minus 5.
Minus 5. So that is your best friend right there. Oh, excuse me. Thank you. He said, bless you. Okay, and so in the numerator, now what do? I want to multiply that guy through, and what do I get on the top?
Oh boy. 3 times the square root of 2, or I
Uh-huh.
guess just 3 square root of 2,
Uh-huh.
minus 3 square root of 5.
There we go. And now can we simplify that denominator a little bit?
Yeah, it's minus
Okay.
3, right?
It's just minus 3. Oh, I didn't plan this out, but check this out. That's kind of cool. Can we factor out a number on the top?
A 3?
A 3. Yeah, I mean, I guess you really need to multiply it out in the first place. But check that out. Like now, in general, this isn't going to happen where everything, like you might have ended up with a 4 and a 7, and then you can't do anything. But I happen to notice, hey, there's a 3 there. There's a 3 there. Oh, and there's a 3 on the bottom. I could go ahead and take advantage of that. So it's not always going to work out that way, but when it does, we should take advantage of it. The 3 cancel, and what am I left with?
A minus square root 2 minus square root 5, right?
Minus, and so here's a way to look
Oh,
at
and then parentheses.
Yeah. And so
Or wouldn't you just do the square root? Because couldn't you distribute the negative?
exactly. And we'd say, and we usually like to write the positive thing out front. You don't have to. We could write this as minus root 2 plus root 5, or if you like, root 5 minus root 2. Right there. However you want to do it. But yeah, I would like, if you end up with something like this, I would like to see one of these be the case. So this happened to work out this way where we had a common factor in here that actually killed the denominator, which is cool. Like, and so we should take advantage of that. But in general, you'll probably end up with stuff that looks like this: 3 root 2 plus, I don't know, 2 root 7 all over 5. And you could see those guys aren't canceling anybody. You can't factor anything out. The 5 doesn't divide a 3. The 5 doesn't divide a 2. So we're done. You can just leave it like that. You're going to end up with, in your homework, one of the oh, can I erase all this?
Yeah.
So in your homework, you're going to have stuff with the only difference here. It will be, instead of just one number on top, you're going to have a sum or a difference of numbers. You might have something like 3 root 2 minus root 7. And it'll say, rationalize the denominator. So you'll know, well, the only way to rationalize this guy is to multiply by his conjugate. And so you do the same thing here. You say, okay, the conjugate is what I get when I flip the signs. Okay, whatever I do to the bottom, I got to do to the top. Like that. And then now it's not as simple, right? And well, I'm just going to go ahead and plug along. We know that the bottom comes out to 2 minus 5. Don't really need to use my brain. That's what conjugates do. The top, now we kind of have to use our brains and go first, outer, inner, last, and all that stuff. First gives me 3 times root 2, and root 2 is 3 times 2. Outer gives me a negative 3 root 2 root 5. Inner gives me a negative root 2 root 7. Last gives me a positive root 5 root 7. And then it's just a matter of simplifying from there. But that's the idea. It's going to look a little uglier there. You want to watch for things that you could possibly cancel. Like if every one of those showed up with a 3 in here, then that would be nice. But that's the idea. Oh, you want your glasses? Here. Here's your glasses. What happened to your face, bud? Must have fallen down. So that's what's going on in your homework. there's a little section on rationalizing the numerator. I did not give you any questions from that, but it's the same thing. It's like, for whatever reason, it might be to your benefit to rationalize the numerator instead. In which case you'd say, oh, given something like that, in order to rationalize this, I would want to multiply by its conjugate. What is the conjugate of this thing right here?
The top one.
Yep.
3 square root 2 plus square root 7.
There you go. And then whatever you do to the top, you'd have to do to the bottom. And so you'd end up with this right here. And that's how you would rationalize the numerator. It's the exact same game. I didn't bother giving you any homework on that. But just so you know, if you're ever told to rationalize a numerator, just talking about rationalizing a numerator, it's the exact same game. So we are almost done. I just want to stress, forget about absolute values from now on.
Okay.
When they come up, when it's a point, when they matter, we'll talk about it. But for this entire homework, you're going to have a bunch of answers in the back of the book that do have absolute value bars, and just pretend they're not there and check that against your answer. And that's what I'm looking for. Finally, just one last thing I want to say on this whole idea of the conjugate of something. This will be huge when we do complex numbers, and the idea is exactly the same. A complex number, like we've talked about briefly, is a number like this, right? So something like 2 plus I times 7 is a complex number. And actually, well, why don't I go ahead and write it as 7 times I? And you can see this is very similar to something like if I had 2 plus 7 times, oh, I don't know, the square root of 2 or something like that. And if I wanted the conjugate of this number right here, I would say, well, didn't really talk about what a conjugate was like when you don't have a root, but let's pretend that we just do the exact same thing. You just write whatever this is, and now what sign goes here in the middle?
A minus.
A minus. That simple, right? I just copy it down exactly, but I just flip the sign. Now, when I do first, outer, inner, last, what do I get with my first multiplication?
4.
Do the outer and the inner multiplications cancel each other out?
Yes.
Yeah, right? Because I copied it down exactly, change the sign. Outer, inner, one's going to be negative, one's going to be positive. They have to cancel each other out. So then, what about the last that I get? What do I get when I do my last multiplication?
Minus 7 square root 2.
Minus what?
Oh, right. Square root 2. Wait. Okay, wait, hold on. 7. And then 2. Wait.
This is what you're doing. 7 root 2 times
7 root 2. So 7. The square root 2 times the square root 2 is just 2.
Right. So
And then
leaves me with that.
7 times 7 is 40. 41? 49?
I think it's 49. And so that I'm not looking for an actual number, but that's the idea, right? Like, and you could see that, yes, even in this context, we weren't sure, but I just said, well, let's just blindly do it. And instead of putting a plus, we'll put a minus. And indeed, it made that root 2 disappear, which was the whole idea. Right? So I think that might also be in your homework. You're going to have, no, it all looks, well, it looks like they give you roots in both cases. But if you were to get something like this, like 7 over 2 plus 7 root 2, and you were told to rationalize the denominator, you do the exact same thing. You flip the sign and you write this, and you just first, outer, inner, last. The outer and the inner cancel. So that all you really got to do is do this times this, minus, because it's always going to be minus, this times this. And when we go to do it with complex numbers, this guy behaves exactly like one of these guys. And it's what we're going to do. As a matter of fact, I is the square root of something. It just happens to be the square root of -1. And so really we're doing exactly the same thing, but that's coming soon. That's coming very soon. We are almost done. I just wanted to do one more thing. It should be quick. Finally, we have something on the top, and in the bottom, we have root x minus root y, and we are told to rationalize the denominator. So I'm going to multiply the top and the bottom by something. What do I multiply the bottom by?
Square root x plus square root y.
So what do I have to use up here?
The same thing.
It better be, otherwise you just change that number. It has to be exactly the same. Now, so we have something up here times this stuff, whatever. I'm interested in what happens in the denominator. First, outer, inner, last gives me what?
X minus y.
Pretty simple. Pretty simple. And because of the way we constructed it, we know that the outer and the inner will always cancel. And I did this just to show you, like, it doesn't matter what these things look like. If x had been, say, 2x plus 1, and y happened to be, oh, I don't know, how about 7y, and we wanted to rationalize this denominator, we would multiply by what on the top and the bottom?
Oh wait. 2x plus 1 plus this, well, yeah, square root of 7y.
And then, okay, that comes out to what? What does my first multiplication give me?
2x plus 1.
2x plus 1. There you go. Outer and inner do what? What happens when you do the outer and the inner?
They cancel.
They do every single time. So don't worry about it. So finally, what do we have?
Minus 7y.
Minus 7y. Okay. I was going to finish up right there, but actually just one thing I want to say, just real quick. Make this slightly more complicated, just a little bit. That instead of square root of 7y, let's say we had square root of 7y minus 1. Okay, so again, we were given something like this, and we had to rationalize the denominator, so I know that I need to multiply by its conjugate. And so I just copied the exact same thing down, but I flipped the sign. First, outer, inner, last gives me what?
2x plus 1.
There you go, 2x plus 1. And then
minus 7y. What? Is that a minus 1?
Yeah, and so here's the thing though, is like we don't want to just write minus and then go 7y minus 1.
Right, you want the parentheses.
There you go. There you go. Right. And so then if we're doing all this stuff, then we'd say, okay, that's 2x plus 1 minus 7y plus 1. And we distribute that stuff. And then we could rearrange it like this and say, okay, that's my denominator and stuff like that. Just saying, got to be careful. Whenever you have a negative, whenever you write down a negative, kind of stop for a second and go, do I need parentheses? In the first case, we didn't because it was just 7y by itself. But when it's 7y minus 1, you better use parentheses just to keep yourself honest. So that's all we are doing this time around. Are you ready for your homework?
Yes.
Okay. All right. This is chapter 7, section 4, on page 308, 309. 308 to 9. Okay, homework, part 1. Numbers 5, 7, 13, 19, 27, 51. 6 problems. Most of them are very easy. This should not take you long at all. This is due at 8 tomorrow morning. Part 2 is a little longer. Not too bad though. 9, 11, 15, 9, 11, 15, 20, 25. 9, 11, 15, 21, 23, 35, 20, sorry, 25, 31, 35. Oh, he's calling for Kayla.
Aw. Hi, Peter.
Just a second, buddy. Just a second. 49. Now, here's the thing. 63 and 64. 64 is the only even one. If you could do 63, which has answers in the back of the book, which by the way, uses absolute value signs that we are not using. But if you do 63 and you see the answer and you go, yep, that's good. 64 is almost exactly the same. And so that should not trip you up. And the final example that we just did was a little bit beyond what 63 and 64 are. So if you look at that last example, 63 and 64 should be really straightforward. This is due at 8 a.m.
Wednesday.
Tuesday, Wednesday. This is due 8 a.m. Tuesday. Part 1 is due 8 a.m. Tuesday. Part 2 is due 8 a.m. Wednesday. I think that's it.